Hi there, I'm going to go through Edexcel's Combined Science 1PH paper, so that's paper 3. It's the physics paper and it's the higher paper, and this is from 2020. First of all, we've got an experiment that a lot of you might have done yourself. So you've got a car rolling down a ramp on a bench, and first of all we've got to describe an energy transfer that occurs when the student puts the car there in the first place. Okay, well, there's various things happening, but you could, for example, say the chemical energy of the student. Okay, so from the student's body is transferred into GPE of the car when lifting. Okay, gravitational potential energy. The student lets the toy car roll down the slope. Describe how the student could find by experiment the speed of the toy car at the bottom of the slope. Okay, well, first of all, if they're going to work out the speed, then they need to at some point calculate distance over time. So the question is, how could they do that? So they could record the distance travelled between 2 points at the bottom. So between 2 points. And this was a 4-mark question, so you need a bit more detail about how you're going to do that. So you could use light gates to measure the time. Okay, and then substitute that into the equation to calculate the speed. Part C. The student needs to develop the experiment to determine the loss in potential energy and the gain in kinetic energy as the toy car is rolling down the slope. State the other measurements the student must make. Well, if they're going to calculate these quantities, then we need to know what the equations are for those. So GPE is equal to mgh, and kinetic energy is half mv squared. Okay, so what else do they need to measure? They've worked out the speed. They also need to measure m, which appears in both equations, and h. So they need to measure the mass of the car, that's m, and the height of the slope, that's h. They don't need to measure g. G is just a constant, 10, that they would use, or 9.8, depending on which value they're asked to use. So just m and h. When the car rolls down the slope, some energy is transferred to the surroundings as thermal energy. How could they calculate that? Well, energy has to be conserved. So the total amount of energy the car had as gravitational potential energy at the top of the slope must be equal to the total in all the different forms at the bottom. So what we can say is that the total amount of energy at the top, GPE, minus the energy that's gone into kinetic energy, the difference between those must have gone into the thermal energy. Okay, so it suffices just to say that the thermal energy is just the difference of those two. Okay, 2A, which of these is a vector? What does that mean, a vector? A vector has a direction. So which of these has a direction? Energy, does it make sense to say that you've got 20 joules of energy up or to the right? No, it doesn't. The one that it does make sense for is a force. Okay, so if I apply a force to an object, I can apply it from different directions, and that causes the object to move in different ways. Okay, so force is the vector. B part 1, state the equation that relates acceleration to change of velocity and time taken. So the acceleration is equal to the change of velocity, so that's the final velocity minus the initial velocity divided by the time. And then we've got to use that equation in the second part. So a van accelerates from the velocity of 2, so that's my u, up to a velocity, so that's the final velocity, v, and it takes 12 seconds. So acceleration is 20 minus 2 over 12, so that's 18 over 12, which is 2.5. Sorry, 1.5 meters per second squared. Now we've got a velocity time graph showing some of the journey there. So calculate the distance the cyclist travels in 15 seconds. Okay, that's just the area under the graph. Okay, and we can see that the shape under the graph is just a triangle. So that's just going to be a half of the base times the height. So a half of 15 times 7. Okay, and if you put that into your calculator, you get 52.5. What are the units? Well, it's meters per second times second, so it's meters. So 52.5 meters. Another cyclist starts from rest, but his acceleration decreases as time increases. Okay, so the gradient tells us the acceleration. So what if the acceleration decreases over time, then the gradient must decrease. So it's going to get a shallower gradient. So it starts off steep and then it's going to get shallower over time. So it might look something like that. It doesn't really matter if it's above or below the first cyclist because you're not told anything about how fast they're going, but just that their acceleration decreases over time. So that you could draw something like that. Okay. Next one, we're told a radio station is transmitting a signal. We've got 97.4 megahertz. So what is that? Okay, what quantity do we measure in hertz? And it's the frequency. So the frequency is 97.4 mega. What does mega mean? Mega means 10 to the power of 6, a million. So first of all, we should write that down. We also know the speed, so that's v, is 3.00 times 10 to the 8. That's just the speed of light. And we're trying to find, well, we're told that the aerial needs to be a length of half the wavelength. So first of all, let's work out the wavelength. We know that v equals f times lambda. So if we rearrange that, we get lambda equals the speed divided by f. So we put that together and get the wavelength. And if we calculate that, we get 3.08 meters. But we're told that the aerial needs to be half of this length. So the length is half of the wavelength. So a half of 3.08, which is 1.54. Okay, so that's the length of the aerial that we need. Okay, next we've got a beam of light being refracted by a glass block and then coming out the other side. And we're asked, how does the student measure the angle of refraction? Okay, so what you should do if you've got a beam of light going into the block like that, sometimes you can see it, sometimes you can't, it depends how faint it is, but then it comes out like that again. And what we need to do, the angle of refraction is this one here. So how can we determine that? Well, first of all, if you were actually doing the experiment, what you would do is you would just draw some crosses on the line going in, some crosses on the line going out, and then join them up. You may have done this yourself before. Okay, all the way up to the block, and then you take the block away. So let's write the steps down. So this is what we need to do, just describe how we're doing this. So draw crosses on rays to draw the rays up to the edge of the block. Then we need to remove the block because we need to join up in between, and we can't do that if the glass block's in the way. So remove the block. and then it's like a dot to dot. So join up the two ends of the rays. Okay, so what we get is like that. Okay, then we need to draw on the normal line. So that's this line here, which was at right angles to where the block was, and measure the angle between the normal and the refracted ray with a protractor. Okay, so there's a full description of what you would actually do. Part C, we've got this radio transmitter which is emitting these radio waves, and there's a boundary in the atmosphere between lower and upper layers of the atmosphere. And what's happening is some of those waves are going up through the upper layer and some are coming back down. So the question is, explain what is happening to the waves at the boundary. And it also says you should refer to these things in your answer, the direction and the speed. So first of all, the waves P, they are being refracted. Okay, how do we know they're being refracted? Because they're moving through the boundary and they're changing direction. Okay, so let's say they're being refracted towards the normal. Okay, so there's the direction. And why are they refracted towards the normal? That's because if that happens, it's because they're slowing down. So that's P. The ones at Q, okay, they're bouncing off the atmosphere, they're being reflected. Okay, so they're being reflected back to Earth at same angle. Okay, so this angle here and this angle here are the same, so at the same angle, but the speed doesn't change when you reflect anything, so the speed stays the same. Okay, so that's still 3 times 10 to the 8 meters per second because it's still moving through the same medium. Right, question 4. A teacher is standing at one end of a field, firing a starting pistol, and the students are standing at the other end of the field, a particular distance away. And what they see is they see the flash from the muzzle of the pistol, and then a short while later they hear the sound. Okay, so it's a sort of a classic experiment to show that light travels faster than sound. So the students do some experiment and they find that the speed is 240 meters per second, but what they find in a data book is that the speed should be 343. So calculate the percentage difference first of all. Okay, so percentage difference is the value that they measured minus the actual value and then divided by the actual value. Okay, and then to make it a percentage we multiply by 100. And if we do that we get about minus 30%. So in other words, their value is 30% lower than it should be. When the distance was 100 meters, the students measured these times. Explain why their times vary so much. Okay, so there's various reasons. So their reaction times are very large compared to the time measured. Okay, human reaction times might be 1/10 or 2/10 of a second, so that's quite large compared to these. And the other reason is that the reaction time is different for each student as well. Okay, there's other reasons as well. So you can see that the different students are different distances away from the pistol. So there's another factor. So let's use that for part 3. Explain one way that the students might improve the experiment. So students all same distance from teacher. And if they're all the same distance, because we're asked to explain here, so we need to explain why that affects the result, why that would improve it. So if they're all the same distance, that removes the error in the time measurement. Well, it removes one source of error from the time measurement, at least. For part B, we've got some loudspeaker in the middle here, and it is giving out sound waves. Draw and label a distance of one wavelength in figure 6. Well, the bits where the particles are close together, they're the compressions. So we draw from one compression to the next compression. And that is the wavelength. So let's label that with lambda like we usually write for wavelength. Describe the motion of the particles as the wave travels through the air. They move back and forth. And they move about a mean position. Okay, so the particles are just moving to and fro in the air as the wave travels. Right, question 5 is all about nuclear physics now. So, which of these describes isotopes of an element? Okay, an element has the same atomic number. So carbon 14, carbon 12, carbon 13, they all have carbon with an atomic number of 6. That doesn't change, it's the mass that's changing. So they all have the same atomic number, so that must mean it's one of these two. And the atomic number is the number of protons, so B doesn't make sense. You can't have the same atomic number and a different number of protons, so it must be the number of neutrons that's different. So A is the correct answer. Question B shows some decay. We've got some protons splitting up into a neutron and some other particle. Which decay is represented in figure 7? Well, protons are positive, neutrons have no charge, so that means that this other particle must carry away some of the positive charge. So it can't be a beta minus. It can't be because that has a negative charge. Gamma doesn't have any charge, so it leaves these two. Well, an alpha particle, that's 2 protons and 2 neutrons. So how can a proton split up into more than it started with? That's nonsense as well. So it must be a beta plus, which is also called a positron. Okay, it's just like an electron but with a positive charge. And part C, half-life of cobalt-60 is 5 years. A school cobalt source has an activity of 38.5 kilobecquerels in the year 2000. Estimate the activity of the source in the year 2020. Okay, so first of all, how many years have passed? That's 20 years. And the half-life is 5 years. So that means that, so 20 over 5 is the same as 4 half-lives. Okay, 5 plus 5 plus 5 plus 5 is 20 years. So 4 half-lives have passed. Now, what is a half-life? A half-life is the time it takes for the activity to decrease by half for a sample. So it must mean that 8.5 kilobecquerels, and it is halved 4 times. So a half times a half times a half times a half. Okay, which is the same as 38.5 times 1 over 2 to the power of 4. 38.5 times 1 over 16. So these are all different ways of writing it. Whichever way you write it, just all you have to do is just calculate that. So 38.5 halved, 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 and halved again gives an answer of 2.4 kilobecquerels. Explain what can happen to the body if a person has a prolonged exposure to gamma rays. Okay, so again, it's an explain one, so we need to state what happens, and then it's like sort of cause and effect. So cells are damaged. Why is that? Because gamma rays are highly energetic, and that can cause, for example, cancer. Okay, so that'll probably be enough to get the marks there. Okay, next we've got an experiment that was done with a Geiger-Müller tube. So we're told a teacher places the Geiger-Müller tube next to a radioactive source. A student starts the counter and the clock at the same time and writes down the readings shown on the counter every 15 seconds. Okay, so after 15 seconds there were about 240. After 30 seconds about 360, and so on. Okay, so that was plotted and then drawn a straight line through it. So calculate the average count rate from the graph. So what we'll do is we'll just take the total count here. So the count rate is going to be equal to, so we're going to use the best fit line here. So that's about 1,760 divided by, well, you can see the first couple of seconds, nothing, according to the line of best fit, nothing happens. So we'll not go 120, we'll go 118 seconds. Okay, so this is 120 minus 2, and on the top it's just 1,760 minus 0. So it's just the gradient of the line between 2 points. That's all we've calculated. And if you work that out, you get about 14.9 counts per second. The student says that the experiment must have been done carelessly because the data seems quite scattered away from the best fit line. The teacher says that should be expected. Okay, why is this? Okay, well, we know that decays, radioactive decays, are random. Okay, so therefore the count rate is not constant. Right, what we got next? We've got an asteroid heading towards Earth, so they send out a rocket to knock it out of the way. Very exciting. So the rocket has a mass of 5.5, I'll write this a bit bigger because it's probably hard to see on the video, 5.5 times 10 to the 5 kilograms, and it's traveling at 14 kilometers per second. So which of these is the correct calculation? So the momentum is equal to the mass, 5.5 times 10 to the 5, multiplied by the speed. Now it's 14 kilometers per second. I need to convert that into the normal units of meters per second. So that's 14 times 10 to the 3. Okay, kilo means 10 to the 3 meters per second. And if I put that all together, I get 7.7 times 10 to the 9 kilograms meters per second, which is C. And then using that equation again, we want to find the speed of the asteroid if we know the momentum. So just rearrange the equation for V. So P divided by M. So 7.5 times 10 to the 10 divided by 8.0 times 10 to the 6. So we find the speed of the asteroid is 9375 meters per second. Okay, or if you want to write it to the same precision as the question, two significant figures, 9,400. Right, the next one is a 6 marker. So we've got a trolley with a spring on and a bit of foil over the top. It rolls down a ramp and it hits a wall, and they've got little bits of foil on them. Okay, foil being conducting, so we can use that to send a signal to an electronic timer. And that allows us to work out how long the little car is in contact with the wall. So the idea is, when the foil first hits it, it starts a timer, and then it bounces, the spring recoils and the trolley moves back up the ramp, and then when it disconnects, the foil disconnects from each other, it stops the timer. So that's the basic idea here. So what we want to describe is how to determine the force, the impact force, how the effective crumple zones can be shown with this investigation, and how we can make sure our results are accurate. Okay, so let's tackle these one at a time. So first of all, how do we determine the force? Well, we need to have an equation. So we need to know that the force is the change of momentum, mv, over time. So we need to say something about how we can calculate this. So we'd need to know the mass of the trolley and the time of the impact. So the impact time. How long is it in contact? I should say contact time is probably a better word there. Contact time. Okay, so that's the first one. That's how we would find the force. How is the effective crumple zones shown in this investigation? Well, what we would do is we'd repeat the experiment with or without the spring. Okay, so the spring is the crumple zone. And we'd see that there'd be a difference in the contact time. Okay, so the spring is acting as the crumple zone. And what would we actually notice? Well, with the spring, we'd expect a greater time. Because the whole idea of a crumple zone is you make the time for impact as long as possible. So from the equation, that means that the force on the trolley or the person in a car is as small as possible, okay, to try and protect them. So that's the second part done. Precautions that may be necessary to achieve accurate results. Okay, so this is just about experimental design. So what might we do? We might repeat the experiment. So we get more than one time measurement for the spring and without the spring. And we need to make sure that we're controlling certain things. So control the angle of the ramp, and when you set the trolley off, don't push it. So we'll write that down as well. And there's probably enough in there to get 6 marks. Right, okay, last question then. And this is an opportunity for you to flex your math skills a little bit. So we've got Newton's third law written in bold here. The force exerted by the rocket on the asteroid is equal and opposite to the force exerted by the asteroid on the rocket. Explain how this statement links to conservation of momentum. So you can do this just mathematically if you know how. So what we've got is that the force is equal. So we'll say the force on the rocket is equal to, but opposite to, so I'll put a minus sign in there, the force on the asteroid. So what's the force on the rocket? Well, remember from the previous question, we said that we can calculate the force by working out the change in momentum over time. So we can say that let's expand that. So that's the final momentum, take away the initial momentum over time. So we're just going to write that down for the rocket and for the asteroid. So we've got the mass of the rocket times the final speed of the rocket minus the mass of the rocket times the initial speed of the rocket divided by the time is equal to minus the mass of the asteroid times the final speed of the asteroid minus the mass of the asteroid times the initial speed of the asteroid over time as well. Now, the times must be the same because obviously the rocket is touching the asteroid as long as the asteroid is touching the rocket. Okay, so the time that they're in contact must be the same in both cases. So what we can do is we can just cancel those on each side. And then we'll rearrange this equation. So let's just write it out again first before we rearrange. So mrvr minus mrur is equal to minus mava, and then we've got minus minus here, so that's plus maua. So then what I'm going to do is I'm going to move this term to the left. So I'm going to add that to the left. And this term here, I'm going to add to the right. So if I do that, I get mrvr plus mava is equal to maur plus maua. So what I've got now is that the sum of the momentum, so the momentum of the rocket and the momentum of the asteroid, so the sum of the momentums, the final momentums, is equal to the sum of the initial momentums. So that's final momentum equals initial momentum. Okay, and that is conservation of momentum then, that the total momentum of the system doesn't change in a collision. So maybe a little bit of a harder question there just to finish off, but hopefully by that point you've done well enough on the paper to get a very high mark anyway. So even if you struggled with that one, it shouldn't make a difference. Okay, if the video was useful to you, please like it and subscribe to my channel. And if anybody would like any one-to-one tuition, then please visit my website, which is www.physicsmathstuition.com, and I'll try and help you out. Okay, bye for now, everybody.